Hi, Mrittika. How
Hi.
are you? And we have
I'm
Samantha. Good. I can hear you.
Good. I'm
And
trying to close browsers and other things.
Good. I think there's just a few buttons I needed to hit to make it all work, and I think I did. So feel free to try sharing screen.
Okay, let me share. I did practice. I practiced.
All right, welcome everyone to the third session of track 2 in the Hot Interconnects tutorials. We have an exciting topic today. It's about microservices and performance tracing, profiling, and analysis of microservice software and hardware. Yeah, so we have two speakers from Intel. Mrittika Ganguli is a principal engineer and director doing cloud-native pathfinding in Intel's network and edge architecture team. She has over 25 years of experience in cloud hardware and software management, network and storage processing control and data plane, cloud orchestration, telemetry QoS, and scheduling architectures. She's active in CNCF and open source initiatives and initiated a service mesh performance index called Meshmark. Very cool. She has an MS in computer science and over 70 patents and multiple IEEE papers in this area. David Cohen is also a co-author, but he was unable to join today, unfortunately, due to personal conflict. So we will hear today from Samantha Alt. Samantha is a cloud software architect at Intel, focusing on solving infrastructure management and operation challenges at scale. By leveraging low-level platform telemetry, she has driven optimizations for performance, reliability, and efficiency of applications and hardware in cloud infrastructures. Her recent focus has been building a large-scale data platform to consume data from sources starting at the hardware level through the full software stack to answer questions related to application and platform performance and carbon efficiency. So I believe we have a jam-packed talk, but I'll just remind folks to queue up their questions in Slack, and we will take questions at the end. So please take it away, Mrittika and Samantha.
Thank you, David. Can you hear me?
Yes, indeed.
Okay. Okay, I have to flash a few disclaimers, and then good afternoon, everyone. I wanted to get started with a picture of a microservice deployment. To set a base from a monolith to a microservice, essentially breaking up our functionality into multiple small functions, which you host as a service. It could be doing one kind of a service, and ideal deployment is a Kubernetes cluster that is hosted inside entities called pods. A number of microservices communicate with each other. There could be a mixed graph that you have on a single host or multiple hosts. To enable the microservice to scale, you would have a network layer 2, layer 3 bridge, which we call a CNI bridge or a container network interface bridge. And to be able to monitor and scale connections and have different policies, you would have a deployment of a service mesh, which would include ingress proxy on a single pod and sidecar with each application. Given this kind of a deployment, what we have seen in our initial studies, that performance goes down quite a bit with the introduction of these multiple layers of infrastructure in front of each of the microservices. And what we have seen is the large number of performance challenges that have come up are tail latency, scalability of application, and utilization of resources, largely CPU utilization, throughput as measured by requests per second, and even network throughput, gigabits per second, has come down quite a bit with deployment of microservices. Network security implementations through TLS takes up a lot of the CPU utilization, and hence enhancements through that require this challenge to be resolved. Given this kind of an environment, the benchmarking and performance analysis is in multiple stages. So modeling of the microservice, modeling of each of the network elements is the focus of this talk here. what I show here is a pictorial view of 3 different types of microservice cloud and edge workloads. The first 2 are example workloads. Specifically, the first one is Death Star Bench, started as a university project and now used in multiple different company environments. What it models is a hotel reservation and a bunch of other services around it, hosted in microservice Kubernetes agent form. And so our focus, again, as the 1, 2, 3, 4 circles show, is the layers at which we will focus our benchmarking and analysis on. So the analysis of Ethernet networking at the NIC, at the CPU, and on the host for the primary network and even the data network. So whether it's a Death Star Bench deployment with a media service, or it is Google Microservices, which is another open source deployment of a boutique ad service with the checkout and cart services and billing services, deployment of that, or at an edge platform environment, we have something called 5G control plane and 5G core network functions, which are now getting containerized. Are they necessarily microservices? Not really, but they're getting there. There are some environments which are breaking them up into simple microservices. And specifically, the 5G control plane services are in a form which talk to each other, with SMF being one service which accepts all the requests. And so that hosted with a microservice, with a service mesh, has shown performance degradation. And so we model 5G control plane in containers, which could be hosted in VMs. So given these 3 kinds of microservices, the focus is around layer 2, 3 networking, the service mesh proxy, the data plane networking, inter-container messages, and overall application simulations. Again, the focus of this presentation today would be largely on the networking layer and not the application simulations themselves. Now, there is previously published data that we looked up upon when we wanted to concentrate on the networking layer and how to model and benchmark that. Google has a paper called Attack of the Killer Microseconds, the networking layer bottlenecks specifically. The paper itself covers all different kinds of performance bottlenecks, but at the networking layer, what this graph shows is latencies are large for RPC and TCP kind of traffic. All others are also there, but we specifically knew that these are the areas which we will see in our smaller environments too. We presented a paper way back in December in IEEE Edge on challenges and opportunities for benchmarking at the edge. And that was a simple experiment of taking Envoy and deploying multiple different kinds of applications on top of it. Calico and Envoy being the layer 2, 3, and layer 7 mesh. And we saw varying kinds of performance degradation from 11% to 4 times the latencies is where we got started out saying we need a methodology for benchmarking. We need some sort of a benchmark out which people can use. Overall, initial analysis, what it showed, and a summary of that analysis was that when you deploy microservices in a Linux environment, the overhead of the Linux TCP/IP stack is one area. And within the stack, it is routing, it is table match, it is lookup, largely given in the IP tables area as one focus. Kubernetes networking environment itself with the CNI is another focus. Higher core context switches. So as traffic enters and you are switching between cores, if you allocate 4 to 5 cores per pod per application, there is a lot of switching happening for servicing requests because it's largely requests coming into multiple applications and responses back. And so core context switches, inter-core transfers, and cache misses were seen if they are deployed at different NUMA domains, specifically if the particular CPU architecture has multiple different NUMA domains. We see them impacting traffic. Security and security performance isolation were some of the challenges. East-west traffic can be largely managed. However, north-south was a bigger impact with multiple traversals of the TCP/IP stack. Given this kind of environment, we concluded we need more monitoring and a better telemetry environment and a collection of data in different forms. And that got a different area of research that Samantha will cover in the next file. Go ahead, Samantha.
All right, thanks. So yeah, when we're talking about the amount of data that we're capturing in this type of microservice environment, you can't do it in a traditional method where you would, run your data collection and analyze it like on a single node. Even when you're trying to deal with like a Prometheus type of infrastructure, dealing with all of the traces and application data and all of the platform data, it's just too much. So you really actually need a full-blown data lake and analytics environment for something like this to really do this effectively at scale. So what is a data lake? Really, traditionally, it's a place where you just look to store a whole bunch of raw data. In our case, we're talking about data that is traces for the microservices, platform data, and logs. And so you can consume data in a few different ways. You could do it through batch or streaming, streaming being the most popular. And then you run it through some kind of ETL pipeline, extract, transform, load, where you modify the data from its original source into something that is consumable by machines, because a lot of these files are not. And then, of course, on top of this, massive amounts of data, you have your, analytics and machine learning pipelines. You have dashboards, and then you have, notebooks and clusters, like EMR clusters, for example, if you're using AWS, to be able to analyze a lot of this data at scale. Okay, next slide. So going over like how we actually built this, our infrastructure is based off of AWS, but you can do the exact same thing in any cloud or on-prem. The idea is that our entire infrastructure is based off of what we consider events. So we won't always be collecting data continuously. It will be collecting data whenever like an experiment is run, like a Death Star bench experiment, for example. The data will start collecting at the experiment side and then start sending it to our environment. So in the streaming scenario, we use an open telemetry monitoring stack, which is an industry standard that I won't have time to go over today, but just assume it's there. So we're collecting all this data through open telemetry. It's coming in through our Kafka streams, which I will talk about in a little bit in a later slide. And then it goes through our ETL pipeline, which is event-based and based off of lambdas and functions, essentially their own microservices. And then all that data is stored, in our database. We use a Presto DB-based database. In AWS, it's called Athena. And then from a dashboarding perspective, we use Superset, which is a way to query using the Presto interface. And then, of course, everyone's favorite Jupyter Notebooks is the other option for data analytics. So we have a feedback loop that comes from once we process all this data, we feed it back to like information to our end users or the services that are currently being hooked into this that says, here's your experiment ID, here's your dashboard, here's how you access this data. And then, they can query it if they'd like. I'll go into a little bit more details in the next slide. So just going another layer deeper, the data ingestion component, we have services that are hooked into the data lake, as well as individual users, like the ability for individual users to send data. We do have data requirements, data formatting requirements. And so the individual users have to format their data in such a way that it can be consumed by our ETL process. So on the services side, which is what Mrittika's project is using, we have 3 different scenarios, right? We have 2 services that are more batch style, and then 1 service that's a streaming style, where we're actually capturing a whole bunch of container information, performance data, trace data, what the servers are actually doing, and then the services. So all of this data is coming in and being consumed through our ETL process. We have different pipelines. I know it only shows 1 arrow, but essentially we have a pipeline for each data type. And there's overlap of data types between the different services, which is nice. But there are some custom ones that are for the microservices streaming, specifically around traces that we work with. So all of this is automatic between the experiment environment and the data lake. It automatically transfers in. The individual users have to invoke it through like a CLI, some kind of command line. And then it all goes into the data lake to be stored. Okay, next slide. So a little bit deeper on the streaming architecture itself. So because the 2 experiment environments and our data lake environment are more disjoint, the way that it works is the experiment environment will send data through their streaming Kafka environment. We will then store it in a source bucket. That source bucket will then trigger our event bridge, which will then trigger our lambdas. So that reads it into our streaming infrastructure, which is based off of Kafka and Flink. What happens is all of the data is being read in this kind of format. It's open telemetry format. I should specify that. It goes in, it gets processed through our Flink environment, and then the new transformed data is stored in a sink. What's called a sink bucket. From our tables and our data backend, we use Glue, AWS Glue. I believe that is going to be the equivalent of Hootie infrastructure, or maybe Hive. We switched between the 2, so I can't remember at the moment. But what this essentially does is that makes sure that all of our tables and metadata have been updated, and it's all coordinated across all the different files, so that when we do query Presto, we are actually looking at the Hive metadata tables to make sure we know exactly where to find all of the data through the queries. I should specify that we do store everything as Presto. What's really nice, or I'm sorry, Parquet. What's really nice about like the new style of like object store based databases is we can actually use these S3 buckets to actually store all of our data. So we don't need to store it in a traditional like relational database. We can use S3 as essentially our database, and it's all in the format and queryable. So queryable essentially S3 files, which is really, really nice in the form of Parquet. So yeah, so we use Hive as a way to update that. So once all the data is updated in Glue, then we're ready to be able to query it. So I guess next slide, we're going to talk about the query itself. So we have some examples. I really just focused on the notebooks because I wanted to talk a little bit about how we structure the data, because like I said, we have data coming from a whole bunch of different types of sources. And from a platform perspective, depending on which platform you run, you're going to get different metrics, which means you can't have a traditional way of storing data with each column being a metric name. So we have to have this stacked format. So we have, some metadata information that's unique in identifying each experiment. And then we have a metric. And as you can see, the metric is in a columnar format, what the event name is, the time, and the value. So you have to do some kind of fancy querying to get the data that you need. But this is how you would want to store kind of unruly data in a queryable format. And then what you would do is once you actually know the data that you want to work with, you would store that in a relational database, right? Because we're talking about, terabytes and terabytes of data. You don't want to be storing that in a relational database. So we call those data marts. It's a data mart infrastructure. So we would take the data that we need in the format that we would want to actually consume it more long-term, store it in a data mart, and then it would be, that's where the dashboards would hook up to. It's really easy to read. It's like an Excel file, essentially, for those who are not familiar with querying. Very columnar. It's nice and easy to use. So I wanted to show an example of that we have to do that because of the data types. And on the right is just an image of some clustering that we did on the performance data that we had. So we looked at how to cluster performance data over time, right? Because we're dealing with time series data. I didn't put any examples of traces in here, but Mrittika is going to have a lot of examples of that. So I just wanted to focus mostly on the performance data coming from the platform. And I think with that, Mrittika, that's my 10 minutes. So I want to hand it back to you.
Thanks, Samantha. I think one of the important things on this graph is the metrics that you're showing here. These are CPU counter data, which we are going to use in the next few files, how to analyze some of that data. So let's go ahead and look at a couple of different areas within the microservice environment, specifically on the layer 2 layer called Calico. And there are a couple of others like Cilium and others, but we have largely looked at Calico, the Service Mesh Envoy, and gRPC. So layer 2.3 forms the basis of the TCP and UDP performance in the microservice architecture. You can say in the infrastructure which hosts the microservice. So this, when we say the stack we looked at before, this is the primary bridge that we want to look at. And this is a summary. So the way I'll show today is first a summary, and then we go into each environment and look at how you set it up, how you benchmark, and how you look at score level scaling data and performance scaling. So this is pre-production Sapphire Rapids platform data around 1 core of Linux performance, so base bare metal Linux performance and million packets per second. The key information to take out from this graph is as you add a bridge, performance packets per second goes down. There are ways to improve. You can bypass the Linux kernel, use the user mode kernel like VPP, but it needs some optimization. So right now, this is what performance it is showing, and we are working on optimizing that and making sure that user mode is beneficial. eBPF as a technology to bypass kernel level routing and lookup has been integrated into Calico and Cilium. And Calico specifically, we have seen it brings back some of the bare metal performance to a level that now you get the benefit of routing and bridging without losing any of the networking performance. Now, there is a Linux kernel level filter that is being built with BPF. It's available actually, but there are CNIs that need to be built with that, and it promises to have much higher performance at the layer 2.3. So we essentially basically want to say this is the base for all microservice environments, a layer 2.3 network stack. Kubernetes networking is not enough. To scale, we need a bridge. And hence, here is how we get started. You know, from a 1 core performance, how many cores do you need to reach 100 gig or 200 gig based on the performance you want to scale up to? And these CNIs, both Calico, Cilium, and there may be a few others that are available on AWS and GCP. I believe the AWS CNI is similar. We haven't benchmarked that, but both of these are available as an option for you to set up your microservice on. So how do we set this up and benchmark? We use very simply iPerf. iPerf as a networking benchmark tool has been used multiple times. Essentially, you set up one server as a client and another as a server, and then you scale applications on Kubernetes environment. So you have 3 modes of benchmarking it. One is the bare metal mode, which is one here, the IP tables mode using Linux networking stack, and then the BPF mode, which is bypassing the networking stack. You can course so that you can measure exactly what is the performance. It's what we are doing. There are a couple of different ways of benchmarking. One is just pod to pod between two hosts, and then pod to pod within the hosts. What I'm going to show as data today is just pod to pod between hosts. And so that looks at north-south performance of the stack. East-west would be another one. How does it scale? How many times you go through the network stack, and how does it scale? So to set your course to the iPerf, and then pod to pod, and then use QoS guaranteed Kubernetes static policy, and bind the iPerf to the course. Given this kind of a setup, you can have multiple combinations. Here is a view of one of those combinations, which we picked particularly to look at a packet size of 1400. Now, Calico itself can be run with a particular TCP MTU size, MTU being the maximum transmission unit that you can set. iPerf has different varieties of packet sizes that you can set it to. The web applications largely are at 1450 or 1480 as their MTU. So if we look at 1400 as a packet size, the three graphs are showing you three different views. Between two different Xeon systems, you can look at what is the one core, one thread performance, and how many cores do you need to scale up to 100 gig. This system was set up with 100 gig NIC, and we were looking at how many cores do you need. And between Ice Lake and Sapphire that we show here, about 8 core, 16 threads is good enough when both of them are running at 2 gigahertz. So we clocked each of the CPUs to run at the same frequency. And at a bare metal Linux performance, around 8 core, 16 thread. But when you installed Calico, you had different performances based on Ice Lake and Sapphire. Specifically, just Calico, the performance is quite a lot down. But once you had eBPF version installed, which is bypassing the kernel, you could see that around 8 core, 16 thread, Sapphire actually helped reach more towards 100 gig. Whereas if I had another graph, I could show 12 core of Ice Lake would actually get us to 100 gig or around 93, 94 gig of performance. Now, this is one view of data that you have between two different Xeons. And again, as you benchmark, you can increase or decrease the frequency. You can get more cache allocated. Sapphire itself had more cache. Here, the performance of this workload does not require too much of memory or other cache bandwidth right now. But as we increase the different kinds of traffic patterns within microservices, we will require that. And so here, that's what is mentioned here. The NIC MTU was 1500, Calico MTU maximum transmission unit was 1450. Now, if you had large packets, jumbo packets, you would require much lower cores to process that if you had a larger MTU. That's one way of doing the layer 2-3 bridge processing. Now, layer 7 includes a couple of different applications. One is the service mesh Envoy. Another is Nginx. I'll cover Nginx as a web server and a web proxy in the later foils. But Envoy is essentially a layer 7 POC proxy, and it's a communication bus. And what it allows is it allows you to create a mesh between your applications. So at the server side, you can have multiple applications hosted in different containers inside pods. And then you can have one ingress proxy on a single pod, and then sidecar proxies to each of your applications. What does this help you to do is scale and also allow you to proxy connections, scale connections, and also scale requests. If you are overloaded on a particular microservice, you can scale out and deploy other microservices. You can have security policies and also logs of your and telemetry being collected for all of your pods, so that you can hook up to the whole environment Sam was talking about. But This adds network hops. So each of these proxies that you're adding, it adds network hops. And so it means more traversals of the network stack. And so benchmarking that would require a particular load generator, which would itself not add its own latency. And so we chose Nighthawk. I have links of all of these at the end. Nighthawk helps in doing base HTTP, HTTP1, HTTP2, and even HTTPS. And so we are running that as 40 threads of Nighthawk on a client system and on a server system. And this is just a simple benchmark with 15 applications. You can scale up to much more. And so the initial experiment is just to look at ingress scaling and then sidecar plus application scaling. Now, summary of what we have seen. So where do we position this performance benchmarking? So this is layer 7, which is the ingress proxy on one of the containers inside a VM or just a container, and sidecar proxies. This is where we are positioning it. Now, microservice environments and the proxy environments are all worker thread based. Each of these proxies have a bunch of worker threads that they schedule. As requests come in, the worker threads are spawned out and onto cores that were allocated to that process. And so scaling of those connections and threads is what gets added to the performance measurements. So for example, if you have this data, which I'm showing is a 12-core allocation to an Nginx proxy, and it was initially giving around 230 milliseconds. And then there are optimizations that were done to bring down the almost around 40%. It was brought down with the kind of optimizations that were done in software and offloads in our future CPU that we are showing here. Now, how did we come about? How did we figure out that there were these bottlenecks, and how did we go about benchmarking? That is what we wanted to show. And then once you apply the optimizations, how do you show back? What is the benefit? It's not just the latency benefit. As you are offloading onto a hardware acceleration, you're actually saving cycles, and you want to feed that back to serving more threads or serving more applications. And so that's something we want to be able to quantify. Either you benchmark for latency or you benchmark for throughput, which is measured in RPS. And then if you are load balancing among cores, are you saving cores by offloading that load balancing? We want to be able to measure that. So that's something I'll show in Nginx later in today's talk. On Envoy itself, I'm giving a very simple picture of what we see in Ice Lake. We did our initial benchmarking in Ice Lake, and this is a latency picture. And what it shows is if you have base HTTP performance with around 8 milliseconds, and then you add Envoy, ingress, and sidecars, your latency goes up almost 3 times. And then if you're able to optimize using eBPF, and then you add HTTPS as instead of HTTP 1 and 2, and that takes up a lot of the cycles. And then we added optimizations with AVX 512 and a few other optimizations and brought down the latency. There were different experiments done for each of these levels. So how did we know eBPF would help? We did experiments around TCP routing. How did we know HTTPS and where to apply crypto acceleration and others? There were other areas of benchmarking done on all of these. And so some of this I'll cover today, some of it maybe in a future talk we will be able to cover that, but the methodology will be the same. Given this whole Envoy environment, and I'm going to skip this whole sample microservice because this is largely just a dashboard. We'll get to Envoy analysis fully. And so what did we do with Envoy after we set that up? Like I was showing with Nighthawk and 2 different systems, we used a tool called vTune, which Intel has to check multiple things. One is hotspots. Once you deploy Envoy and ingress proxy, you give 1 core to each and look at the performance of that and look at how applications get scaled. Are you able to scale number of pods? Are you able to scale worker threads of the proxy itself? And then you slowly increase the number of cores. And so increase the number of cores allocated to front proxy, and then look at if there are bottlenecks at the application or the clone. Specifically at the Envoy front proxy or ingress proxy, these terms are used interchangeably. Is the main thread able to handle connections? Is the kernel able to load balance connections? Once the kernel is load balancing connections, are the CPU utilizations for each worker thread uniform or uneven? And where is the unevenness, and what can we do to solve that? So going down the path within vTune is very easy to look at hotspots and isolate that. Kind of metrics which Sam was showing in the counters, those counters will come up within the Envoy screen. Specifically looking at clone scaling or microservice application scaling, you increase the number of services. Once you have increased the number of cores on ingress and sidecar, can you increase the number of microservices and look at, does utilization improve? And so clone scaling and core scaling and worker thread scaling, these are some of the different experiments that we set up. And this is a dashboard of some of those. So what did we see? When you have just one core allocated, you're largely centered around Linux kernel scheduling. And it's largely functionable around that. And you're not hitting any other, whether it is one core on front proxy or one core on the clone and sidecar. As soon as you apply multiple cores, you see the bottlenecks are around connection tracking, thread scheduling on both the ends, and then Envoy itself comes up as a higher cycle user. So this is 1,000 QPS. There are experiments where we scaled 1,000 to 100,000 QPS on one system, and so we looked at that too. But this is showing you a dashboard of vTune and how you can go down within vTune to look at bottlenecks and specifically address those. Another sort of analysis that we did was the counters, the CPU counters that are collected through the telemetry system. You can do something called a top-down analysis, and top-down or TMAM is quite popular within our environment. What you can do is the top-down analysis for only those cores which you want to focus on. So if you know the core numbers for the ingress proxy and you want to look at only that. For example, here the graphs and the legend below show core 8, 9, 10, 11. These are the cores which we focused on to look at how they scale. What happens when you increase the number of microservices? Both the graphs are showing increase of microservices from 0 to 40. What happens as you increase the number of microservices and the number of cores to the microservices? What we see is that the proxies become more front-end bound. System becomes more front-end bound, meaning it's largely just doing context switches and moving data, moving the requests. There is no processing happening on the core as of yet. As we increase the number of requests and messages which are reaching, and then the size of messages as we increase from 1 kilobyte to more, or we increase the number of messages, gRPC messages or other messages, and there is message processing happening, it will become core and memory bound. And so initial benchmarking would show front-end bound and less usage of the core, and there will be bottlenecks around L1 and L3 misses, largely L1 and L2, I would say, and then it becomes L3 and memory bound. You don't reach memory bound often if your system has enough memory that the whole socket supports. You are largely front-end bound for most microservices and microservices with service mesh. And so there are optimizations which can be done to fix that. There are deployments which can be done to improve that. Now, once you've done the TMAM, you can also extend it to doing analysis of many other parts of the CPU counters. So if you do see that it is memory bound or cache bound, then you can go and look at cache misses, size of cache. If you see it is core bound and analysis of the core and what type of application it is doing, you can do that. Now, what we did was we next looked at the vTune analysis of all the three setups that we had. And can we do a summary of where is the bottleneck largely on? So one core, multiple clones, or one core sidecar, one clone, or multiple core, multiple clones. What are some of the trends that we can see on vTune? We saw Linux forwarding, and that's something that is focus that we get from Linux kernel. Entry Linux switching, that's very common. Linux scheduling, libc, those are areas of bottleneck for the second and the third. And then within Envoy, match functions, Envoy uses scheduling, and so the libp thread scheduling impacts Envoy performance too, because it uses that. Watermark was another is a technology within Envoy, which is used to manage the connections internally. And so this gives us an initial view of where we should go focus our optimizations on and improvements on, and then look at other areas. And so we looked at whether eBPF could help in Linux forwarding. We know that. And so now there are other service mesh environments coming out where we have ourselves released one with eBPF, and then there are others that are coming up, which will. When you have static matches, if there are regex matches, you can optimize it using Hyperscan, high-end regex matching solution in software that we have implemented. There is since this is eventing based, Envoy uses lib events and eventing based. We used a combination of event FDs with an offload in our CPU called DLB, Dynamic Load Balancer, and I'll cover that in a minute, which helped in improving some of the scheduling and load balancing of the cores, and that improved the CPU utilization. So this is a methodology we have been using for other applications too, and we have used within Envoy. And we haven't yet released all the solutions, but some of the software optimizations are out there. I haven't covered TLS. There is a whole analysis on TLS and how TLS is used within an SSL library in Envoy. And that will be a topic for another discussion. Within the open source community, CNCF, Container Networking Forum, we have a project called Service Mesh Performance, and different companies are part of it. Red Hat, Google are some of the engineers from those companies are part of it. We have created a tool called Meshery, and Meshery is a tool where you can model different microservices and their service mesh environments. So you can have an Envoy deployment, you can have a Linkerd deployment, you can have all of that, and you can look at whether it is beneficial for your own environment or not. And then once you have that as a view within Meshery, we introduced an index called Meshmark. This has been just introduced this year, like three months ago in Service Mesh Con. And this is, we would like to invite more people to take part in it. This is largely to measure efficiency of the service mesh deployment. Now, some environments actually look at efficiency from a performance viewpoint. Some look at efficiency from a budget viewpoint. Am I requiring more resources to deploy the service mesh? So does this fit within my budget? So performance within a budget. So that's something which they would look at. Some else look at how easy it is to deploy, if they have a way to measure the ease of deployment. And so there is a sample calculation that has been proposed. It's very loose right now as a calculation. It's utilization classes with usage efficiencies, MUEs, and you can put weights to that. So for example, if for you, the resource utilization is higher in weight, you can put higher weights on that. Whereas utilization class responsible for budgets, if that is higher for you, can give a higher weights to that. Now, what is the MUE, mesh utilization efficiency? A very simple example is something we introduced and we looked at is CPU cycles and CPU usage utilization. If your MUE is nearer to 1, we would say your utilization is efficient and your mesh deployment is efficient. How do we measure that? It is the MUE to latency relationship. So is your MUE able to tell you that your environment is efficient if your latency is low? So as your latencies are low, by the blue line here, it shows when latencies are low, your yellow line efficiency is higher. As your utilization, as your MUE is showing higher, your utilizations are lower. These two are pretty related. And how do you impact that? It's how the deployment impacts that is all going to be based on the kind of analysis we are doing. Can you really improve your utilization through the MUE index? That's something we aim to continue to work on. Okay, so now let's look at another area of focus, which is, and then I'll bring back a section of this will be on Nginx HTTP performance largely, but this is the third angle for microservices, which is messaging between the microservices. So between microservices, you can use JSON for messaging, or you can use gRPC messages. And gRPC is RPC framework from Google, and it has a mechanism to send out messages in a format called protobufs, and protobufs can be encoded, decoded. The performance characterization of gRPC also has not just the network stack, because it will be carried over HTTP. It also has the transport of gRPC, which will be largely serialization and deserialization. So there are different angles and different areas of benchmarking within the gRPC environment. And so we looked at, there are many benchmarks. We have been running many of them, GHZ being one very popular one, DistiBench is another, which is a very extensive benchmark, and then HyperProtoBench for protobuf benchmarking. And so very simply, what we saw in our first experiment, and others who have been doing have seen the same, is where is cycle spent largely? Network, of course, and that's why we focused on network analysis as we started. ePOL, many of the microservices and proxies use ePOL. And then Greeter is just a hello application. And the others consists of some 20 other small areas. So we ignore the portion which is others, and we focus on network, Greeter, and ePOL. Greeter being the application without network and ePOL part, we wanted to look at that and look at what are the areas of where cycles are being used. And so you see language runtime, whether the messages and the language used is a Go or a C++ or a Rust or a Node.js. So multiple language. And so language runtime is a big area of focus and benchmarking. And then protobuf. Protobuf, encode, decode, serialize, deserialize, all of that. So there is a whole area. This itself could be a separate 1 to 2 hour talk on what you gather from it. But this is one area of focus for us, and I'll share just a few more ideas around that. Like, for example, we did protobuf profiling, and we looked at serialization, deserialization of different types of messages. The message numbers which are shown here are of different sizes. And specifically for large sizes, we have seen the deserialization number of cycles used is much larger than serialization. This is on an Ice Lake system, and the right-hand side is on a Cascade Lake system, which is the older one. Encode, decode actually uses much more, nanoseconds per operation. So that became then a focus of us to figure out why and look at how to accelerate that within the system. But being able to isolate each of these messages and then each of these areas that itself is an area of benchmarking that is going on. Now, how are these gRPC messages used inside an application? Like if you choose a microservice like Death Star Bench and look at gRPC usage there. There may not be a whole lot, but you can look at what happens when you use between microservices and what areas. That's something we can again look at in a future talk. But specifically, this is within HyperProtoBench. And so then we said, let's look at how many cycles it it uses up in a system. This is system 1, where we looked at a flame graph, and this was generated by Linux tools to generate. There is a pprof, which helps you. So you use perf record, and then you use pprof to visualize the flame graph. There is a very good tool that we have now as part of Intel called Granulate, and I think you had a talk by Granulate within this forum, which helps you to do flame graphs in cloud. And so this is how a flame graph would look like. And I've specifically highlighted the flame graph, which shows one of the messages around 10.3%. The deserialized cycles used is 10.3%. And then an optimized version where, or a better, IPC system, and I call it system 2. I didn't have approval to show which CPU this was, but essentially this was showing, benefit, a little bit of benefit, and how you can see that in a flame graph. Besides VTune, and now VTune allows flame graphs, but just a year back, you could do flame graphs separately, and then you could do VTune separately. But you could see, in the flame graph, how much time each of these different types of messages are taking up, how much CPU cycle time, and improvements within that. Now, if you did improve the network stack, it would show up somewhere high up here, and we can see that in future talks also. So this was just an introduction to gRPC analysis. I think we will definitely come back sometime and do a more deep dive on gRPC. So now let's look at a little bit detail on Nginx. It's a very good tool for looking at HTTP performance. It's a complete server. You can initialize it as a proxy and also as a web server. We model it as an application as behind a service mesh, and we also model it separately and look at HTTP, HTTP2, HTTPS performance. So I'll cover a little bit of just HTTP2 specifically with the CDN workload. So with the CDN workload, what we saw is CDN workloads have video, audio, text. They are of different sizes, and as Nginx worker processes allocate each worker thread on a core which is servicing either video or audio, they are unbalanced, and hence you may have text reaching and being deployed, being rendered on a web browser much earlier than video. Now there are optimizations that Google Chrome have done on their side. They allow you to prioritize the traffic on the browser, but on the web side, there is much more required to be able to make, first of all, improve utilization of the cores which are doing just text, and also balance it out. And so that was not possible with what Nginx had. It does do connection load balancing, but core cycles load balancing wasn't available. And so we introduced that first in software, and then we have the load balance offload solution in our Sapphire Rapid system. And so we utilized that to look at how much performance benefit you could get. And then we also did another solution where you could do prioritization. So if you want the video traffic to be prioritized on a particular core versus audio traffic to be prioritized, you could do that all within this hardware block. This is essentially a queuing system inside the CPU core, and ports attached to each core. And when you have large traffic, so you do get some amount of load balancing from NIC to core using RSS. But if you have large traffic, then you can use DLB to offload that. This is showing a setup of the whole experiment. So you have the main server, which is shown here, CPU 0, CPU 1. You have the content server, which is serving up the audio, video, text files. And then you have WRK used as the HTTP test generator. And we did 2 sets of experiment. Before getting to Nginx, we built a simple web server, which is 12 cores or even less than that. You can initialize it as 2 cores and increase up to 4 and 12. And so what we saw is within that simple web server, whether you did software offload and when you did a hardware DLB offload, you were able to improve performance 30 to 40%. which is on the left-hand side. And then that was keeping the number of connections the same. With the cycle saved, if you fed it back to the client, you can actually service more connections. Around 66% more connections was possible between just the software version and the DLB offload version. Now, this is within our sample in-house web server, and that is available if anybody wants to experiment with it. Connect back with me and I will make it available for you. Now, we applied the same to an Nginx solution. And since Nginx has a much more extensive environment where you can do many different kinds of traffic patterns, and also you can look at latency for different size of packets and different size of files being retrieved. There is, if you're retrieving from an NVMe device, the latency of the NVMe device or the storage will be there also. If you're retrieving from the host file, of course, that will be faster. But if it's a web server which is retrieving from a storage which is dependent on NVMe, that it will have its own delays. But this was simple from the same host, and the large benefit is when you have large file sizes, 1 megabyte file sizes, and you have 40K connections. So if it is around 1 million operations per second, you get large benefit from DLB offloads. And so that's something that is getting introduced in Nginx, and being able to profile and figure out, it's the similar pattern we saw in Envoy, Linux scheduling and the usage of cores. It's almost the same within vTune that we saw that. And so this solution was implemented to get the benefit. Okay. Now, another environment was where we wanted to look at remove the kernel network, because that was the one big hog, and let's use a user mode stack. What is the user mode stack that we used? And there is an open source project called FIDO or FDIO, and that has it's called a VPP. And within FDIO, there's a project called VPP, and it's extensively used in the telco and edge world. A lot of customers deploy that, and it has it's a graph based, and it's a vector packet processing environment. That's why VPP, and it has a graph based software model, and it has its own host stack. So we integrated Nginx with VPP, and then we looked at the DMA transfers within that environment, and then used a data streaming accelerator environment to accelerate the DMA. So we had that as an experiment for more than a year or so to look at how can we scale with the same number of cores, how can we scale the performance, looking at kernel scheduling and then data movement. And so that was an environment which has been tested here, benchmarked here with 200 gig NIC cards, 2 systems. This is again on Sapphire, one of our CPU environments that is right now in pre-production. The initial vTune analysis, this is a screen from vTune directly. On the top, it would show a summary, and you can always go down and look at the different counters, CPU counters. But on the top, it will show, it's a 30-second experiment essentially. And it will show you CPI, which is cycles per instruction, and a few other things. But most importantly, the topmost function, which is showing the largest amount of CPU time, is the memory copy function, the move 512 blocks. And so that then became an area of focus and to look at. And that's how we said, okay, let's look at, after VPP integration, that was the area where we said, okay, let's look at how to improve that using a data streaming acceleration feature within Sapphire. Now, I have included all the links on what is DLB, what is data streaming acceleration. And again, anybody who wants to know more, please connect with me. But how did we measure, actual benefit? So the first thing is you increased the data sizes from 1 kilobyte and above. Since this is a data copy acceleration, we started with 1,000, 1 kilobyte kind of an environment, 1,000 byte, and increased that, and looked at what is the Nginx kernel performance versus kernel out and user mode VPP plus kernel plus Nginx, and then added the DSA acceleration. And so around, you'll see around 16 kilobyte, the improvements with using a hardware accelerator goes up quite a bit. And it's more than, I think, more than 70-80% that this specific environment is showing. But you can, in your environment, you can get more than 30-40% of benefit is in an actual environment. This is a specific controlled environment. But what we do is we allocate number of cores to VPP, we allocate number of cores to Nginx, and then change those. You do see latency benefits also. Latency in this last 64 kilobyte is quite a bit. It is around 45% of latency benefit here. So in the kernel mode, we're using 4 Nginx core plus 1 extra kernel stack core. But the kernel actually ends up using up more than 1 core because it's the same process space as Nginx. And so you really cannot bound the kernel to 1 core, right? Whereas when you use a software, user mode software like VPP, you can do 2 VPP or 3 VPP and increase the number of cores on VPP and Nginx. So this is one view of performance gain. The other view is to look at between VPP software and VPP software with DSA, what is the benefit we are getting using a offload for memory copies. And so there we saw, almost, if you see this last, this is around 12 cores and this is around 8 cores. So we got a benefit of around 4 cores by using an offload environment. And the vTune shows the memory copy is no longer the topmost here. Okay, so I think we are reached almost the end of our talk, but I just wanted to summarize that a microservice environment has multiple bottleneck environment to be benchmarked, and then you can apply solutions to each layer. But unless you have the complete view of each layer, you won't be able to see benefit. You do need a large telemetry and data lake environment to collect and do traces, and then formulate your total solution. Proxy-less and combined proxy meshes are coming up, offload to other environments like SmartNICs and IPUs. So that would be our next steps. And I have links and others included within the PPT here, and anybody wants to get in touch with me. I know we didn't have time to do any questions. I'll probably leave it to David to address that.
Yeah, I don't see any questions in the Slack channel, but yeah, please feel free to put those. And yeah, we are just a couple minutes over. Maybe I could just ask one quick verbal question since it's kind of puzzling to me. I'm really interested. I think it was some vTune measurements, right, that showed that in particular thread scheduling, right, is overheads are very high in some of these microservice architectures. And I'm wondering, maybe I missed it, but did you get to the bottom of that? It almost seems like, threads don't have enough work or something like that if the scheduling is.
You're right.
So
yeah. So what was happening was if people allocate in Kubernetes, they allocate number of cores to that ingress proxy. And so as soon as you allocate, multiple worker threads are scheduled. And that's also configured. So people may say ingress with 15 threads, and they'll just get allocated.
Yeah.
And they're just waiting. And so that's why it's showing. So many times it's just waiting for more requests. And they don't, if there is more on a particular thread, it doesn't get moved over to the other thread. Now, if you do that moving over, you'll be data copying. And so that's why that is a big performance hog.
Interesting and surprising, I suppose. Yeah. Okay. Yeah. Again, everyone, please don't be shy and ask questions in the Slack channel. And yeah, I suppose we could end there and move on to the next session. Thank you very much, Mrittika and Samantha. That's an incredible amount of interesting information and measurements.
Thanks, David. Thank you,
so much
for this opportunity.
Yeah.
Same.
Have a good one.
Have a good rest of your day. Bye.
You too. Bye now.